Hello and welcome back to Math Class in Session. Today, derivatives of exponential functions. Let's take a trip into history for a moment and meet Mr. Leonhard Euler. Leonhard Euler from the 18th century, a Swiss mathematician. He came up with a very special number, the number E. That was one of his many contributions. While researching him, I came across Project Euler, and I would highly recommend it to anyone who's interested in mathematics. Pretty interesting stuff there at projecteuler.net. So let's find this natural number E, discovered by Leonhard Euler. It's a natural number, and you'll find out why later. For now, let's fill in this table of values. If n is 1, this expression, 1 plus 1 over n to the exponent n, is 1 plus 1 over 1, which is 2 to the 1. And if n was 2, then this is 1 plus 1 over 2, which is 3 halves squared, 9 quarters, which is 2.25. And if n was 3, then this would be 3 plus a third, that's 4 thirds cubed. That would be 64 over 27. And my calculator says 2.37. And if n was 4, this would be 5 quarters to the exponent 4, 2.44. And if n was 5, this would be 6 fifths to the 5, 2.49. And let's start taking bigger leaps. Suppose n was 10. This would be 1 plus a tenth. That's 1.1 to the exponent 10. 1.1 to the exponent 10 is 2.59. Now let's look at what these y values are doing. It started at 2, and it's increasing. As n increases, it's increasing, but more slowly. Just looking for patterns. If n was 50, this would be 1 plus a 50th to the exponent 50, 2.69. That works down on the calculator. And if n is 100, we're taking bigger leaps now. 1 n plus 100th is 1.01 to the exponent 100. And it's hardly increasing anymore. It seems to be reaching a number. If n was 500, taking a bigger leap, 1 plus 1 500ths to the exponent 500 brings us to this number. And let's do 1,000. If n was 1,000, this would be 1.001 to the exponent 1,000. 2.72 again. So it seems we've reached a number. And in fact, by definition, E is the limit as n approaches infinity of 1 plus 1 over n to the exponent n. And that number is a decimal number. It's the number 2.71828, and it goes on forever without a pattern, very much like pi does. Let's recall what an exponential function looks like. Y equals 2 to the x. Looks like this blue line. We can check it by subbing in 0 for x, and y would be equal to 2 to the 0, and that's 1. And so we see that y is 1 there. If x was 1, this y would be 2 to the 1, that's 2. So we see that if x is 1, yes, this is 2. This is the graph of y equals 2 to the x. Recall it from previous studies. And its inverse, which will be its reflection across this line, y equals x, looks like this. And it's y equals log base 2 of x, the inverse of y equals 2 to the x, inverses. If we simply replace the base 2 with base e, so instead of 2, it's 2.71. Now it doesn't change too much. Y equals e to the x. And its reflection, its inverse, y equals log base e of x. They would look like this. Still with the same y-intercept and x-intercept, still with the same asymptotes. It's just the base is now e. Log base e of x has a nickname. Y equals log base e of x is otherwise known and very popularly known as y equals ln x. It's just y equals log base e of x. So when you see ln x, think log base e of x. Ln x. It's called the natural logarithm. So I've brought the graph forward of the natural logarithm and y equals e to the x, and let's just take a look at some of the properties of these two graphs, these two functions. Y equals e to the x has a domain. We can see that there's an arrow on the left here and there's an arrow on the right, and it covers all of the x values. So x is any real, while y equals ln x, we can see that the domain, it has to be greater than 0. Domain greater than 0. And so remember, we can't take the ln of a negative number. Take a look at the graph. X is always greater than 0. So the domain is x is greater than 0. Can't take the ln of a negative number. Because that's really saying, well, what exponent do you put on e to get something negative? There's no exponent you can put on 2.17 to get something negative. Range of y equals e to the x, we can see the range starts at 0 and then goes up. So anything greater than 0 is the range. While the range of the ln function, we can see that it has an arrow on the bottom here and takes off to infinity in that direction. So y is any real. Now, since they are inverses of each other, we're not surprised that the domain of y equals e to the x is the same as the range of its inverse, while the range of y equals e to the x is the domain of its inverse. That doesn't surprise us. We note that y equals e to the x passes through 0, 1, while y equals ln x passes through 1, 0. E to the ln x equals x. I put this on the list because it's a tricky fact that seems to come up a lot. Ln x, by definition, is the exponent you put on e to get x. That's the definition of ln x. The exponent you put on e to get x. And it's being put on e, so we'll get x. Here's another tricky fact. Ln e to the x is x, because this says the exponent you put on e to get e to the x. The exponent you put on e to get e to the x. That's what this ln e to the x means. And of course, the exponent you put on e to get e to the x is x. Y equals 0 is a horizontal asymptote for the exponential function. X equals 0 is a vertical asymptote for its inverse, y equals ln x. Let's take a look at this y equals e to the x and see if we can find something special about it. If we pick this point, we note that its y value is 1. We know it's 1 because x is 0 and anything to the 0 is 1. And if we draw the tangent to the curve at that point, there's the tangent to the curve at that point, and measure the slope of the tangent, we can see that you say start from this point, rise 1, run 1, rise 1, run 1, rise 1, run 1. The slope of the tangent to the curve at the point when the y value is 1, the slope is 1. Let's pick another point. How about this point? We see that the y value here on the blue line is 2. And if we draw the tangent to the curve through that point and measure the slope of it, well, let's measure the slope. Starting, say, at this point, rise 2, run 1. The slope is 2 because it's 2 over 1, rise over run. Okay, so if the y value is 2, the slope of the tangent is 2. If the y value is 1, the slope of the tangent is 1. And trust me, if the y value is a half, which is about at this point, the slope of the tangent would be 1/2, because the slope of the tangent to this curve, y equals e to the x, is the y value of that curve. And that is one of the reasons I think that e is very important, because it's its own derivative when it's the base of an exponential function. So the derivative of y equals e to the x. If y equals e to the x, then y prime equals e to the x. Very easy to differentiate. Let's do some examples. Differentiate the expressions. Okay, solution. Use the fact that y equals e to the x implies that y prime equals e to the x. And we'll also use the fact that y equals e to the f of x implies that y prime equals e to the f of x times the derivative of f of x. Because, after all, this is just a chain rule. Here's an example. Y equals 3e to the 5x. Want to prime it? All you do is copy it times the derivative of the exponent. And then tidy it up. Here we go again. Want to differentiate this? All you have to do is copy it and then multiply by the derivative of the exponent on e. So it will be copy it times the derivative of the exponent on e, 6x minus 5 in this case. Let's go again. Want to differentiate an expression? Okay, well, we have to recognize a product of functions of x. This is 3x squared, that's a function of x, times e to the x squared plus x. That's also a function of x, an exponential function of x. A product rule gives us first thing prime times the second thing plus the second thing prime times the first thing. So the first thing primed is 6x times the second thing. That's what's happening here. Plus the second thing primed. So we'll have to look at this, copy it, times the derivative of the exponent, times the first thing. So what we have is the first thing prime times the second thing, plus the second thing prime, which goes as far as here, times the first thing. And we like very much to find critical numbers. We'll still need to optimize expressions. These expressions will now contain an e, so we'll be interested in finding critical numbers. To do that, we'll need to factor. So multiply it out first, very carefully. This will be 6x cubed times e to the x squared plus x, plus 3x squared times e to the x squared plus x. Looking at this result, we can look for common factors and notice that 3 and x and e to the x squared plus x are common to each term. Take them all out, divide them out of each term, and it's the process of common factoring. I rearrange the trinomial, and one might consider whether or not this trinomial will generate any critical numbers. It won't, because it's got a negative discriminant. However, there is one critical number when x equals 0. A final one. A glance at this function tells us that its derivative y prime will be 7e to the x times 2x. So it'll be 14x e to the 2x. But I did it by using Leibniz notation. Why? Because other people do that, and one needs to be prepared to negotiate different people's styles. So d7e to the x squared by dx equals d7e to the x squared by dx, and I slid the dx over. I'm going to use the chain rule. So anything I put here in this numerator, as long as it matches what goes in this denominator, is valid. And what one does is chooses x squared. Put them, dx squared in each. And so we'll differentiate this with respect to x squared, which means simply copy it times the derivative of x squared with respect to x. Which is no surprise to us. We knew this already. And a final example, find the slope of the tangent to the curve at the point. Very typical calculus question. Here the curve is y equals e to the 2x over x squared, while the point is at the point where x equals 3. Solution, do not sub in x equals 3 first. I just mentioned that because at this stage, many calculus students think that it might be a good idea to sub in the x equals 3 first. No, one must differentiate first. And it's a quotient rule. So top thing prime, which is a copy times the derivative of the exponent times the bottom thing, minus the bottom thing prime, which is 2x times the top thing, over the bottom thing squared. One needs to get used to the fact that if there's a multiple in each and every term of both numerator and denominator, it can be divided out of each. So we can take this x and divide it out of this term and this term and this term and get this. So the x has been divided down. It's just 2x e to the 2x, or 2e to the x times x. The x is now absent from this term, and this term has become x to the 3. And one might say, well, why don't I just sub in 3 now? And that would be completely acceptable. Myself, I'm partial to factoring it first because I know that we'll be interested in critical numbers later, and factoring is a good exercise. So I factored it, and now we'll sub in 3 and answer the question. Y prime of 3, and we have our slope of the tangent to the curve at the point. Please note, very rarely do we turn e into its decimal. E is an entity which is widely recognized in almost all sciences.